everyone. This is Babitha, working as Assistant Professor in the Department of ECE in Institute of Aeronautical Engineering. In this session, I'm going to discuss about the problems related to the feedback amplifiers. So in this feedback amplifiers, we are going to calculate the overall gain of the feedback amplifier and bandwidth provided by the feedback amplifier, and also the gain with feedback. Without feedback, how much gain we are getting in the amplifier, as well as after adding the feedback, how much amount of gain we are getting in the case of feedback amplifiers, and how much feedback ratio we are utilizing to provide the feedback back to the input signal, and how much amount of distortion is reducing in the feedback amplifier, and also the calculation of input output resistances. So these are the parameters we are going to calculate in the case of feedback amplifiers. So before going to the problems, I'll revise why we are moving for the feedback amplifiers even though we are having the amplifier circuits. So in the case of normal amplifier circuit, when we are providing the input signal, it will provide the amplified version of the applied input signal here. Okay, but along with the amplified signal, it will also provide some distortion as well as noise levels across the output here. So in order to remove that noise as well as distortion levels in the amplified output, we are adding feedback to this amplifier circuit. And also we can improve the amplifier parameters by adding the feedback here. That is nothing but input output impedances variation as well as voltage and current gain variations also will occur when we add feedback to the amplifier circuit. So in this particular case, I am considering the general structure of feedback amplifier. If suppose we are not providing feedback, means this is the amplifier only. For this we will apply the source signal and we will apply the output signal to the load. So for this amplifier, input voltage we are applying here, it is V in, and the output voltage we are getting here, it is the V naught here. So if we see the only gain of this amplifier, we will get it as ratio of V naught by V in, that is without feedback here. So if we utilize this particular amplifier, I have already mentioned, we may get some distortion as well as noise levels, and we may not reach the required amplifier parameters across the output. So in order to overcome that only, we are adding feedback to the amplifier circuit. So in order to add the feedback to the amplifier, we are having some procedure here. What is mean by feedback here? Feedback is nothing but we have to take some portion of the output signal from the amplifier, and again that portion of the signal we need to give back to the input of the amplifier here. So while doing such process, we require two things here. One is sampling and one is mixer here. So sampling is used to take some part of the output voltage here, and always we will do the sampling across the output of the amplifier. So by sampling process, we are getting some portion of the output voltage. That output voltage again we are giving to the feedback network here. Okay, so this output voltage from the amplifier acts like an input voltage for the feedback network here, and the output from the feedback network is the feedback voltage. Here the parameters may be either voltage or current depending upon which input we are providing for the amplifier. If it is current, means we will get it as current IF. If it is voltage, means we will get it as voltage VF here. So this particular feedback voltage, again we are giving back to the input of the amplifier through the mixer circuit. So the function of the mixer circuit is to mixing the feedback signal as well as source signal whatever we are providing. So it will take these two signals and the combination of the two signals as the input signal it will provide for the amplifier. So because of this process, we can able to reduce the noise as well as distortion across the output of the amplifier and also improve the amplifier parameters. So when we calculate the gain with feedback amplifier, in that case it is the ratio of V0 by Vs here. Okay, V0 by Vs. Why? Because if it is a feedback amplifier, the input signal is the Vs signal, not the Vin signal. So where Vs is nothing but Vin plus or minus Vf here. Okay, here we may add or subtract the feedback signal from the input signal. That is depends upon which type of feedback we are utilizing in this particular case. So if it is plus means we are adding positive feedback. If it is minus means we are adding negative feedback to the circuit. So that's why from the mixer we will get it as the signal Vin plus or minus Vf here. So that particular signal again applied to the amplifier circuit. So this circuit is the simplified version of this particular block diagram here. So simply in the case of feedback amplifier, we will present with the amplifier as well as the feedback network. Okay, actually for the amplifier we are providing the input signal as the sinusoidal signal like this. Okay, and when we are applying this signal to the amplifier circuit, we will get the output like this. And the same signal, the same output signal again we are giving back to the feedback network. So again the feedback voltage also in the form of sinusoidal signal we are getting here. And here we will get it as Vi plus or minus Vf signal to the amplifier circuit. And here we are also having some parameter, that is beta, that is nothing but feedback ratio here. So that feedback ratio is nothing but the output of the feedback network is Vf and the input of the feedback network is V0. So Vf by V0 is the feedback ratio here. And just we will discuss about the sampling and mixing process here. Why? Because if we use the voltage, the sampling is different. If we use the current, the sampling is different. So sampling is nothing but taking some part of the output and we are giving back to the input of the circuit. So it is always we are performing at the output side of the feedback amplifier. Suppose the output signal is voltage, means we have to go with the voltage sampling, so that we have to make the connection between the output and the feedback as the shunt circuit or parallel circuit here. So in this way we need to connect the output signal to the input of the feedback network. Suppose our output signal is the current signal, means we have to do the current sampling. In that case, we have to go with the series circuit. It is nothing but directly. In this way, we need to giving back to the input of the feedback network. And similarly, if we perform the mixing operation across the input of the amplifier, that will do the addition or subtraction of the feedback signal with the source signal here. And always mixing will perform across the input of the amplifier. So here mixing also depending upon the input signal is voltage or current here. So if it is voltage signal, means we are going with the voltage mixing. So that is nothing but the feedback signal coming from the feedback network as well as input signal to the amplifier are connected in series here if it is voltage mixing. And if it is current mixing, means we need to go with the shunt mixing. That is the feedback signal as well as input signal are connected within parallel here. So these two are very important, sampling and mixing processing in the case of feedback amplifier, that is depending upon the voltage and current signals. And depending upon the sampling and series process, sampling process as well as the mixing process, we are dividing the feedback amplifiers into 4 categories. So those are, if we use voltage sampling and series mixing, that particular feedback amplifier we are calling it as the voltage series negative feedback amplifier. So when we are writing the feedback amplifier, either we need to go with the sampling first, mixing next, or else one more case is mixing first and sampling next. Okay, in these two ways we can represent the feedback amplifier. So this representation is the sampling mixing, that is output side to input side. So this particular voltage series amplifier, we can also call it as shunt feedback amplifier. Sorry, series shunt feedback amplifier. Why? Because if we are going with the mixing sampling means, so here voltage means output signal, voltage sampling means this is output side. Okay, and series mixing means this is input side. So mixing is input side. So mixing is input side means input side which type of operation we are performing, series here. So that's why series. And sampling, voltage sampling means how we need to connect here in the parallel connection or shunt connection. So that's why it is series shunt voltage amplifier or feedback amplifier here. So always in the sampling, voltage means shunt connection and current means series connection. And similarly in the mixing, voltage means series connection, current means shunt connection. These are the basic things required to identify the different topologies of the feedback amplifiers. And the next one is if we use current sampling and series mixing. So in that case, we can call it as the current series negative feedback amplifier. So that is output to input. That is nothing but we are performing current sampling and series mixing here. So we can also write it as in terms of mixing and sampling here. So mixing, which type of mixing? Series mixing. So that's why first we are taking series. And current sampling means what? Current sampling means we have to go with the series connection. So that's why it is also series here. So we can also call it as series negative feedback amplifier when we go with mixing to sampling. And next up, if we use voltage sampling and shunt mixing. So in that case we can call it as the voltage shunt negative feedback amplifier. So we can also call it as, from mixing to sampling, if we take this shunt mixing means, so first we write it as shunt, and sampling, which type of sampling we are using? Voltage sampling. Voltage sampling means again shunt connection. So that's why shunt negative feedback amplifier. And the last category is if we use current sampling and shunt mixing. So in this case, we can call it as the current shunt negative feedback amplifier. And when we go with the mixing and sampling means, shunt mixing means first we will get it as directly shunt. And current sampling means it is series connection. So it is series, shunt series feedback amplifier. So in this way, we need to identify the different types of feedback amplifiers. So now we'll move with the problems related to this feedback amplifiers. In the top, first one is an amplifier has a mid-band gain of 125 and bandwidth of 250 kHz. If 4% negative feedback is introduced, find new bandwidth and gain. And also, if the bandwidth is to be restricted to 1 MHz, find the feedback ratio, that is beta. So in this problem, the gain value is AV. Gain is 125 and also given bandwidth value. Bandwidth is 250 kHz. It is the ratio of highest frequency to lowest frequency. And from this, the first bit, if 4% negative feedback is present means how much amount of bandwidth and how much amount of gain we can expect from the given feedback amplifier. And also, if the bandwidth is 1 MHz only, if it is restricted to 1 MHz, how much the feedback ratio. So these are the parameters we need to calculate here. So for that, I'm going with the first bit, that is finding of the voltage gain. this one. So voltage gain with feedback here we need to calculate. Here AV means voltage gain without feedback. AVF is voltage gain with feedback. So I'm going to calculate the voltage gain with feedback. The formula for formula for this is AV by 1 plus AV into beta. So where AV is the open loop voltage gain and beta is the feedback ratio here. So here AV value is given in the problem, that is 125. 1 plus again it is 125 into beta value is given it as 0.04 here. So if we calculate it, we will get it as 20.83 as the gain with feedback here. Okay, and the next we need to calculate the bandwidth, how much amount of bandwidth with feedback we are getting here. The formula is 1 plus AV beta into the given bandwidth here. So here 1 plus AV value is 125 and the beta value is 0.04 and the given bandwidth value is 250 kilohertz. It is 10 power 3 here. So if we simplify it, we will get it as bandwidth with feedback is equal to 1.5 megahertz. So with feedback, the bandwidth is increased to 150 megahertz from 250 kilohertz here. And while coming to the second bit, in the second bit what we need to calculate from the given bandwidth. The given bandwidth with feedback is 1 megahertz. So if it is 1 megahertz, how much it is the beta value we need to calculate. So for that purpose, bandwidth feedback equal to 1 plus AV beta into bandwidth here. So 1 plus AV is 125. We don't know the value of beta here. And the given bandwidth is 1 megahertz. 1 into 10 power 6. So beta value in this case is 0.024. Okay, beta. Sorry, here it is 1 into 10 power 6 and this bandwidth value is 250 kilohertz. So if we simplify it, we will get the new feedback ratio is 0.024 here. Yes, while coming to the second problem, an amplifier has an open loop gain is 1 lakh. A negative feedback of 10 dB is applied. Find voltage gain with feedback and value of feedback fraction MV here, and we can also call it as beta here. This feedback fraction we can also call it as beta or MV here. So here the given parameters are the open loop gain without feedback is 1 lakh and negative feedback of 10 dB is introduced. So with feedback, the value is 10 dB, 10 decibels is applied. So in this case, we need to find feedback. Here it is. We need to find voltage gain with feedback and also the fraction of feedback we need to calculate here from the given values. So first one is voltage gain with feedback we need to calculate. Voltage gain with feedback in decibels we need to calculate. Why? Because the feedback introduced in decibels. So that is 20 log 10. The given open loop gain is 1 lakh. Okay, so we can write it as 20 log 10 power 5. So the value we will get it as 100 dB here. Okay, the voltage gain with feedback is 100 dB here. And next, we find voltage gain with, this is the gain without feedback. So we need to calculate voltage gain without feedback. This much we are getting 100 dB. And voltage gain with feedback, if we calculate, it is 100 minus this 10 dB. We need to subtract here. So total 90 dB here. So now we can write 20 log base 10 gain with feedback is equal to 90 here. Because of this dB, I am adding 20 log here. So this AVF is equal to 90 by 20. So this value is 4.5 here. Log base 10. So here log base 10 AVF. So if you want to find only AVF, we need to apply anti-log with the value 4.5 here. So that value we will get it as 31622. So the gain with feedback value is 31622 here. And the second bit we need to calculate here is feedback fraction, how much we are getting with this feedback. That is, we can calculate from the gain with feedback formula, that is open loop gain by 1 plus open loop gain into MV here, or else beta. So AVF value we got here it as 31,622 and AV value given it as 1 lakh. 1 plus AV value again given it as 1 lakh. Here it is MV. So after simplification, we will get it as 2.17 into 10 power minus 5 as the fraction of feedback here. So in this way, we need to calculate the feedback fraction as well as the gain with the feedback in the case of feedback amplifiers. So this is the formula we need to remember in this problem. And welcoming to the next problem. For a voltage series feedback amplifier, they already mention voltage series feedback amplifier. That is nothing but it is voltage sampling and series mixing. Okay, voltage series feedback amplifier, or we can also call it as series shunt feedback amplifier. Okay, so from this given amplifier, we have to find distortion, how much amount of distortion it is providing, and gain with feedback, and also the input impedance as well as output impedance after introducing the feedback into the circuit here. So from the circuit, I can write it as the source resistance given it as 1 kilo ohm and the collector resistance given it as 4.7 kilo ohms. And the emitter resistance is given it as 100 ohms. And from this, we need to find the distortion D, gain with feedback, input resistance with the feedback, output resistance with feedback. See, from the amplifier circuit also, we can able to derive all these parameters. But after introducing the feedback, how much amount of variation is there, we are going to see. So in order to solve this problem, we need to do some steps here. In the first step, we have to identify the topology of the given circuit here. So first step is identify the topology of the given circuit. So how we can identify the topology here? by short circuiting the output voltage. Why I am telling it a short circuit means the given in the circuit output as the voltage. So that's why if we short this output voltage, that is nothing but V0 equal to 0. If this V0 equal to 0, the feedback signal must be also 0 here. So in this case, this particular condition is satisfying here. Why? Because here V0 as well as Vf both are across the Re resistance only. If V0 is 0 means obviously Vf is also 0 here. Okay, so that we can say it as the, so V0 equal to 0 and Vf equal to 0 means it is the voltage sampling circuit. The given circuit is the voltage sampling circuit. And also we can see feedback signal Vf is subtracting from the input signal Vs here applied to the base of the transistor. So here this signal is subtracting and it is the current signal. So we can call it as the series mixing. So that's why it is called as voltage series circuit or series shunt circuit here. Okay, so this is the identification of the topology of the given circuit. And in the second step, we have to find the input circuit as well as the output circuit in order to find the given parameters. So the thing is find input and output circuits. So to find the input circuit, V0 must be 0 here. So once the V0 is 0 means, if V0 is 0 means Vs is in series with the Rs resistance. Okay, this supply voltage Vs is in series with the Rs appears between the base and emitter of the transistor. So this particular voltage is not present means these two will come in series and those are appear across the base and emitter terminals of the given transistor here. Okay, so to find the output circuit, we have to make the input current as 0. Why? Because input signal we are taking here it as the current. So once the I1 current is 0 means obviously the base current IB is also 0 here. So if these two currents are 0 means RE appears only in the output loop. So there is no connection between the input and output circuit, though IB current is 0 here. So we can draw the simplified circuit from these assumptions, that is transistor with the source resistance Rs and with the supply voltage Vs. Okay, and the output is short circuited, so that's why emitter resistance is also not present. And once we are considering the input circuit, these two resistances will come in parallel. That is the collector resistance as well as the emitter resistance. But output we will measure across the RE resistance only. This is emitter, base and collector terminals of the transistor, and here the input current is flowing and here we are measuring the output voltage here. So from the assumptions at the output side, that is V0 equal to 0, and assumptions at the input side, that is IB equal to 0, when we are assuming these two conditions, our circuit will become like this. So from this circuit we need to calculate the parameters. So in order to find the parameters, first of all we have to replace this transistor with a hybrid equivalent circuit. That is the step 4. Replace the transistor with its hybrid equivalent circuit. So from the circuit we can say this is the common emitter configuration. Why? Because emitter actually common between the base and collector terminals. So we have to take the H parameter or hybrid model of the common emitter circuit. So we are having the HIE input impedance and also HFE IB here. So this is the H parameter equivalent model, And along with this, we are also having in the circuit the source resistance RS externally connected, and Vs voltage is also externally connected to the circuit. And across the output side, we are having the series combination of the collector resistance as well as the emitter resistance. RC and RE here. V0 we are measuring across RE. And I1 current is flowing here. So this is the emitter, base and collector of the transistor. Okay. And the input impedance from this side we are calculating, and the output impedance we are calculating from the output side of the circuit here. And next, first thing we need to calculate here, it is open loop voltage gain. Once we find the open loop voltage gain only, we can able to find the remaining all the parameters of the feedback amplifier. So that's why I am finding the open loop voltage gain. So open loop voltage gain AV equal to the ratio of output voltage by input voltage. Open loop means we are not providing or we are not considering the feedback signal into account. So in that case, it is output by input voltage only, not the feedback voltage. So here output voltage from this circuit, we can write it as this HFE IB into RE resistance. That is nothing but HFE IB into RE resistance, and the input voltage is nothing but the source voltage Vs. This is voltage gain or open loop voltage gain without feedback. Here I am considering it as the first equation. And next, to find this value, I am applying KVL to the input loop. Across this input loop, I am applying KVL here. So if you apply KVL to the input loop, we will get the source voltage value. That is, we are having two resistances in the input side, RS as well as HIE. So we can write II into RS plus HIE here, or else II or else IB. Input resistance or base resistance, both are same. RS into HIE here. So substitute this Vs value in the first equation. Substitute in equation 1 to find the voltage gain. So AV equal to HFE IB RE by IB RS plus HIE. Okay. So here you substitute the values. So HFE value of the common emitter amplifier is 50. We know that. And the emitter resistance value is 100 ohms given in the problem. And the source resistance value is given it as 1 kilo ohm. And again HIE value is 100 kilo ohms. Sorry, HIE value is 1.1 kilo ohms. So if we simplify it, we will get it as 2.38 as the open loop gain here. And next, we need to indicate the output voltage as well as the feedback voltage, and from that we need to calculate the beta value here. Actually, this output voltage as well as the feedback voltage both are present across the emitter resistance. Both are across the output voltage, both are across the output resistance RE. So both are having the same values. So the feedback ratio or feedback factor is the ratio of feedback voltage to the output voltage. Why? Because output from the feedback network is VF and input for the feedback network is V0. Here both are same, so we will get it as 1. So beta value we are getting here it as 1 here. And next we need to calculate all the remaining parameters. Those are distortion, input resistance, output resistance as well as output resistance with feedback. Okay, so to calculate that, first of all I am going with the distortion, that is 1 plus AV. Beta is the formula for this. So in this case, if we substitute the values, 1 plus AV given it as 2.38 and the beta value is 1 here. So if we calculate, we will get it as 3.38 as the distortion level in the feedback network. And if we calculate the input resistance RA, so only if we calculate the input resistance of the amplifier, that is the series combination of the source resistance as well as HIE resistance. Because in the input circuit we are having only these two resistances. That is RS is 1 kilo and HIE is 1.1 kilo. So it is 2.1 kilohms. But if you want to find the input resistance with feedback, that is RIF. So in that case, this is RA into D value, that is RA into 1 plus AV beta. So this D value we have already calculated. So RA value we got it as 2.1 into 10 power 3 into this value is 3.38. So if we simplify it, we will get it as 7.09 kiloohms. This is the input resistance with feedback. See here, this is the input resistance without feedback, that is 2.1 kiloohms. But after adding the feedback, it is increased to 7.09 kiloohms. Almost 5 kiloohms is improved in the case of input impedance by adding the feedback to the amplifier circuit. And next, we need to calculate the output resistance of the amplifier circuit, that is R0 dash by D value. So how we can calculate this R0 dash? R0 dash is nothing but the resistances which are present in the output circuit. In the output circuit, we are having only single resistance, that is RE here. So this value is 100 ohms. And to find the output resistance with the feedback, that is RE by D. So that is 100 by D value is 3.38. So it is 29.58 ohms. ROF. See, if we observe these two resistances, this is the output resistance without feedback. This is the output resistance with feedback. So here it is decreased from 100 to 29.5. Almost 70 ohms is decreased here in the output resistance. Always, in order to operate the amplifier in the proper way, the input impedance must be increased, the output impedance must be decreased. So by adding the feedback, input impedance is increasing and the output impedance is decreasing here. That is a basic advantage of the addition of the feedback to the amplifier. While coming to the next problem, an amplifier is required with a voltage gain of. So the given values I am writing AV equal to 100, which does not vary by more than 1%. So the variation of gain is 1%. If it to use negative feedback with a basic amplifier, the voltage gain of which can vary by 20%. So determine the minimum voltage gain required as well as the feedback factor here. Okay, we need to find the gain as well as the feedback factor from the given values. So to calculate the gain value, I am taking two values we have to take here. With 1% change, how much gain we are getting. With 20% change, how much gain we are getting. So if we compare the two values, we will get the final voltage gain. So for that purpose, I am taking open loop gain as 100 first. That is 100 equal to AV by 1 plus AV beta here. Okay, gain with feedback, first I am taking it as 100 here. So I am writing this equation as, after cross multiplying, 100 equal to 100 into A beta equal to AV here. So this one I am considering it as my first equation. And also we can write it as 1% variation, means I am taking 100 minus 1, that is 99 equal to AV by 1 plus AV beta. So here if 1% variation is there means in this case the variation in the gain is 0.8. Okay, it is given in the problem itself. So 0.8 AV into beta here. So we can write it as 99 equal to 99 into 0.8 AV beta equal to 0.8 AV. So this one I am taking it as the second equation. And next, to simplify these equations, I am multiplying multiplying the first equation with the 0.792 here. That is multiplying 1 by 0.792 here. 792 times AV here. So if we multiply in that way, we will get it as 7.92. This equation 7.92 equal to 7.92 AV beta equal to AV here. So this side also 0.792 AV. So this is the third equation I am taking here. So next I am subtracting this second and third equations to find the AV value. So subtract 2 and 3 here. That is nothing but after subtraction we will get it as 19.8 equal to 0.08. So 008 AV. So AV equal to 19.8 by 0.008 here. So after simplification it is 2475. The gain value is okay. And substituting this gain value in the equation 1. So substitute this one in equation 1. That is this particular equation to find the beta value. So if we substitute in that equation 100 plus 100 into 2475 into beta, we don't know, and this AV value is again 2475. So from this we will get beta as 0.0096. So we have calculated the gain as well as beta values here. So in this case we need to calculate these two parameters AV and beta. So we have calculated here it as AV as well as beta here. And next, coming to the next problem, an amplifier with open loop voltage gain AV given it as 1000 with a variation plus or minus 100 is available. It is necessary to have an amplifier where voltage gain varies by not more than plus or minus 0.1%. So from this we need to find the reverse transmission factor beta and also gain with the feedback. These two values we need to calculate here. So to calculate this beta as well as gain with feedback, I am taking the variation of the gain as well as variation of the gain without feedback. That is DAF by DA equal to 1 by 1 plus A beta into DA by A. This is the relation we already discussed in the feedback amplifier concepts. So here the variation of the gain given it as 0.1, 1 by 1 plus A beta, and here the variation of the open loop gain is 100 by 1000. So here we will get it as 0.1 into 1 plus A beta into 1000 is equal to 100 into 100. So if we simplify, we will get it as 1 plus A beta equal to 100 and A beta equal to 99. And from this, beta equal to 99 by A value is given it as 1000. So it is 0.099. If you write in terms of percentage, 9.9%. That is the beta value. And next, we need to calculate the second parameter, that is gain with feedback, by using the formula AV by 1 plus AV beta here. So here we know all the values now. AV is given it as 1000 1 plus 1000, and beta value just now we have calculated 0.099. So if we simplify it, we will get it as gain with feedback as 10 here. So in this way, we need to calculate the feedback ratio as well as gain with feedback in the case of given feedback amplifier. So in this session, we discussed the different problems related to the feedback amplifiers. In that, how to calculate the voltage gain, input output impedances, and how to identify the topology of the given circuit, and then how to find the parameters from the given circuit. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.